Hey, Calc BC. Today we are going to start 6.6, Alternating Series Part 1. This is in our unit all about series convergence. It's the first half of College Board's Unit 10, and today we're going to be covering Lesson 7 and Lesson 9, Alternating Series Test for Convergence. That's the convergence test we're going to learn today. And we're going to determine absolute versus conditional convergence, which goes hand in hand with the alternating series test. We're going to come back in 2 lessons for the ratio test, but 9 really goes with 7, so that's why we're pairing those together today. The alternating series test is a method to determine whether an alternating series converges, much like all of our lessons in this unit. And we're also going to be learning about absolute versus conditional convergence. A series may be absolutely convergent, conditionally convergent, or divergent. If a series converges absolutely, then it converges. Makes sense. If a series converges absolutely, then any series obtained from it by regrouping or rearranging the terms has the same value. That is something that we're going to be studying throughout this lesson. Okay, so this will all make sense. And again, this comes straight from College Board, so we're going to be covering all things that you definitely need to know for our course and for the AP test. Let's switch over to the notes. All right, here we go. So 6.6, alternating series part 1. An alternating series is a series whose terms are, as you may be able to guess, alternating. They switch between positive and negative. So here are some examples. And the sign that this is usually the case is within the series notation. If we have a -1 to some power that has n in it, because think about what that's going to do to the terms, right? As n goes up by 1, we're either going to be multiplying whatever's left by +1 or by -1. So the sign is going to switch every time. And it doesn't necessarily have to be a power of n+1 or a power of n, as you see in these 2 examples. It just needs to be some exponent that makes the sign switch every time. And here is another fact that we need to know. In general, just knowing that the limit as n approaches infinity of a sub n equals 0. Now, I want to be clear that this is referring to the limit of the sequence. So remember back from the first lesson in this unit when we were talking about sequence versus series, right? So if the terms of a sequence approach 0, that doesn't tell us about the convergence of the series. However, it turns out that an alternating series must converge if the limit of the sequence is 0 and the terms decrease in magnitude over time, which leads us to the alternating series test. We'll go over this test, and then I'm going to show you a visual that will hopefully make sense of that short paragraph right there. So alternating series test. Let a sub n be greater than 0. The alternating series with either version of these alternating signs, either the first term's positive or the first term's negative followed by alternating signs, either of these converge if the following 2 conditions are met. 1, the limit as n approaches infinity of a sub n equals 0. So the limit of the sequence terms is 0. And 2, the terms are decreasing. So a sub n plus 1 is less than a sub n for all n. In other words, a series will converge if its terms 1, alternate in sign, 2, decrease in magnitude, and 3, have a limit of 0. Decrease in magnitude means we think about like the absolute value of the terms. So if we kind of ignore the fact that the signs are alternating, just look at the terms themselves without their sign, and those terms need to be decreasing over time. And it needs to be approaching 0. If all 3 of those things are true, then this series converges. Let's take a look at a visual. And this is on the back of the notes if you have this printed out at the top. If an alternating series converges to a sum S, then its partial sum jumps around S from side to side with decreasing distances from S. The figure below shows the first 4 partial sums of an alternating series which converges to sum S. So think about this line right here as a number line, and we're visualizing as we add all of the terms of this series together. So a sub 1, a sub 2, a sub 3, a sub 4, those are all the terms of our series, and we're one by one adding them and kind of figuring out where we end up on this number line after we add them. So if we start at 0, let's assume a sub 1 is positive, we end up somewhere over here. Then we subtract a sub 2, we add a sub 3, we subtract a sub 4, and the idea is that we know that each of these terms, a sub 1, a sub 2, a sub 3, a sub 4, is decreasing in magnitude. So none of these terms are ever as big as a previous term. So that's why an alternating series always converges if the terms are decreasing in magnitude, because think about a sub 3 right here. We know that a sub 3 is smaller than a sub 1 and a sub 2. A sub 3 cannot get this sum to ever go past the initial term. So like we're already bounded in here. A sub 3 can only get us somewhere in this range. We can't ever go past and try to like approach infinity. It's just not going to happen because of the fact that this is alternating and the terms are decreasing in magnitude. So there's always going to be some sum that we're approaching over time because of the nature of this kind of sum. So hopefully that makes sense. I can explain it in more detail at some point if you ask, but that's kind of what we're working with here. So now we're just going to assume that this is true. So we're going to check these 3 things, and if all 3 are true, then this series converges. But what about divergence? Note, this does not say that if the limit as n approaches infinity of a sub n does not equal 0, the series diverges by the alternating series test. So think about what that's talking about. This is, again, that sequence. So it's the sequence terms. If they don't approach 0, we can't say the series diverges by the alternating series test. The alternating series test can only be used to prove convergence if the limit as n approaches infinity of a sub n does not equal 0, the series diverges by the nth term test for divergence, not by the alternating series test. And if we look back at our chart, that's the very first one on our list. I think it's technically the second convergence test that we learned. The nth term test, we know that the series diverges if the sequence terms don't approach 0. And this can only be used for divergence. Even if these terms are alternating and it looks like we're going to be using the alternating series test, if we discover that the terms don't approach 0, it diverges by the nth term test, not by the alternating series test. And you can see where we have alternating series on our chart. One of the comments is that this test cannot be used for divergence. So we do not want to make that mistake, okay? Okay, so let's actually try this and see what happens. Letter A. Determine whether the following series converge or diverge. The first thing that we're going to do here is try to separate out the part of this series term that is causing the alternating series to happen. So we're going to try to pull out the -1 part, and the rest of it is going to be, a separate part. So we'll have the series from n equals 1 to infinity. That -1 to the n plus 1 is causing the series to alternate, but all that's doing is switching the sign every term. It's not really changing anything else. So then that's going to be multiplied by n over 2n minus 1. So now that we can see that this is definitely alternating in sign, we are going to test out all 3 of these pieces to the alternating series test. So I'm going to check. Are we alternating? Are we decreasing in magnitude? And do our terms have a limit of 0? We've already shown that's alternating, right? This is kind of switching the sign between positive and negative. This fraction isn't going to be changing the sign. It's always positive because we only have positive n's that we're plugging in. So that part is true. That's all we need to do for that. Next up, we need to check, is this magnitude decreasing? So ignore the +1, -1 component here. We're just going to check this fraction and make sure that it's decreasing as n increases. Now that's going to be potentially tricky. I can tell because the denominator has 2 times n, the denominator appears that it's going to be growing a lot faster than the numerator. But I think this would be a good time to show you, just in case you're not sure if we're decreasing just by looking at that fraction. There's a way we can prove it, and I'll show you. So what we're going to do, it's kind of like we saw up here, a sub n plus 1 has to be less than a sub n. That's kind of like the way we can prove this. So we're going to plug in n plus 1 for the n. So let's just say a sub n is n over 2n minus 1. Then a sub n plus 1, we're just going to make a generic, next term in the series by changing all of the n's to n plus 1s. And let's see what happens when we kind of multiply and combine like terms here. So we'll have n plus 1 over 2n plus 2 minus 1, which is n plus 1 over 2n plus 1, okay? And so we want to be able to compare this to this. So what I'm going to do is try to find this numerator in this numerator, trying to find this denominator inside of this denominator. In other words, we're going to have n plus 1. And on the bottom, we're going to have, let's see if we can make 2n minus 1 happen. So if we have 2n minus 1 that I'm pulling out of this denominator, I took the 2n out. I had plus 1, but I need it to make a minus 1. So I'm going to add 2 afterwards, because negative 1 plus 2 is going to give us plus 1. And I'm going to try to show that that's less than the original. And hopefully you can see that every time we're adding 1 to the numerator, but adding 2 to the denominator. So our denominator is growing larger than the numerator is. So that is indeed correct. We are decreasing. A little complicated. We don't always have to do it that way, but it's good practice when you can't tell naturally whether the terms are going to be decreasing. So we are alternating. We are decreasing. Last step. Are our terms approaching 0? So let's see if we can check that. We know this is just going to keep switching signs between positive and negative. So let's just check this fraction again. We can do the limit as n approaches infinity of n over 2n minus 1. And if you think about Bo-Bo-Bot needs DC, we have exponents that are the same. So we divide the coefficients, we end up with 1/2. And that is not 0, right? We're approaching 1/2, not 0. So that is actually false. So this series does not have terms that approach 0. So if we check back on our chart again, if the terms don't approach 0, then we are going to diverge by the nth term test. So this original series, so I'm going to write out the original series. So that series diverges by the nth term test. All right. And that is all we need to write there. We've shown that this limit equals 1/2. So the terms don't have a limit of 0. So we diverge by the nth term test, not by the alternating series test. Let's take a look at letter B. All right, in letter B, we have a new series here. I'm going to once again pull out the -1 to the n. That's the part that's making the signs alternate between terms. And even though I'm pulling it out, I'm still writing it after the series, the summation notation, because it's still part of each term. I'm not pulling it out in front like we sometimes do with integrals, because it has an n in it, so I can't just take it out. All right, so this time we're looking at a magnitude of 1 over n squared. So I want to know, is this alternating? Well, I can already tell it is based off the fact that we have -1 to the n. Is it decreasing over time? Are the magnitudes decreasing? If I wanted, I could compare 1 over n plus 1 squared, and that's pretty clearly less than 1 over n squared because the denominator is bigger. So that's definitely decreasing. And do we have a limit of 0? Okay, and I would say pretty clearly that we do. I could write it out if I wanted. The limit as n approaches infinity of 1 over n squared does in fact equal 0. We can tell because the denominator is growing, the numerator is staying the same. So check, check, check. All three things were true. So this converges by the alternating series test. Let me write out the original series again. Okay, there we go. So that converges by alternating series test. So there's an example of when this might cause divergence. And remember, we use nth term test for that. And then we have a example where we converge by the alternating series test. So this brings us to a couple new definitions. Absolutely versus conditionally convergent. And here's how this works. The sum of a sub n is absolutely convergent if the absolute value of the terms also converge. But we're conditionally convergent if our series, which might be an alternating series, converges. But if we take the absolute value, so we remove the signs switching, change all the signs to positive, and we add all the terms together, if that diverges, this is conditionally convergent. Okay, so let's take a look here at an example. Determine whether the given alternating series converges or diverges. If it converges, determine whether it is absolutely convergent or conditionally convergent. So we're first going to notice that this is alternating. It even tells us that in the directions. So we're going to try to show whether this converges or diverges using the alternating series test. So I'm going to separate out the -1 to the n. And it turns out like this. And I want to know, does this alternate? Well, definitely. Is it decreasing? Are the terms decreasing in magnitude? So we look at the 1 over the square root of n, and that's definitely going to be decreasing over time. I could write it out up here if I wanted. I could do 1 over n plus 1 to the 1/2 is less than 1 over n to the 1/2, which is definitely true because the denominator is bigger. So that's decreasing. And are our terms approaching 0? And yeah, that's going to be true too. I could write that out over here. The limit as n approaches infinity of 1 over square root of n equals 0. Check. So based on those three things, we could say we converge by the alternating series test. But we're not done yet. If it converges, which it does, we're going to determine whether this is absolutely convergent or conditionally convergent. So let's take a look back at our initial series. We are going to try to take a look at the absolute value. So I'll write this out in a couple steps. You don't have to write this all every time. But if we're taking a look at the absolute value of our series, in this case, that means taking the absolute value of that initial version of the series, which really just means we're chopping off the -1 to the n, right? So we're just going to be left with 1 over the square root of n. And let's think about all of our old convergence tests. Can we decide whether 1 over the square root of n converges or diverges? This is a p series. The exponent, or the p, would be 1/2. So this is n to the 1/2. And since p is less than 1, this diverges, right? I could even rewrite this one more time if you wanted to, so that we can really see the p. So this right here is a divergent p series because 0 is less than p is less than or equal to 1. And therefore, the original series is conditionally convergent because the alternating series converges, but the absolute value diverges. So we just call that conditionally convergent, and the condition is that it's alternating. That's the condition that makes it converge. So we can say the sum from n equals 1 to infinity of -1 to the n over the square root of n is conditionally convergent. Okay, and we've already kind of stated all of the tests that we used. So in our final statement, we don't need to state any sort of convergence test. We already did all of that work. Okay, so there's one other thing we're going to look at today. We don't have to write anything else down, but this is just a property of conditionally convergent series. So let's just read this together. A finite sum, such as 1 plus 3 plus 5 plus 7, can be rearranged without changing the value of the sum, right? If I did 1 plus 5 plus 3 plus 7, it still has the same sum. That's a property of addition that you learned a very long time ago, that you can switch the order and you still get the same sum. But did you know that is not necessarily true of an infinite series? It depends on whether the series is absolutely or conditionally convergent. If a series is absolutely convergent, every rearrangement has the same sum. However, if a series is conditionally convergent, it can be rearranged to have any sum, which is crazy. So let's take a look at an example. The alternating harmonic series. So we already know what the harmonic series is, right? It's 1 plus 1/2 plus 1/3 plus 1/4. If we take a look at the alternating version of that, 1 minus 1/2 plus 1/3 minus 1/4, etc. It's conditionally convergent and can be shown to have a sum of the natural log of 2. We can rearrange the series to have a different sum. Consider the following rearrangement. So let's examine this. So we are going to take all of the terms, 1 minus 1/2 plus 1/3 minus 1/4, and we're going to rearrange them. So you can see we're just kind of like moving around the order of the terms. So instead of the denominators going in order from 1, 2, 3, 4, 5, 6, 7, 8, 9, etc., it's going to go 1, 2, 4, 3, 6, 8, 5, 10, 12. It's the terms are in a different order, but just trust me, all the terms are here. Okay, and the signs are still alternating in the original context, right? Every even denominator has a minus in front. Every odd denominator has a plus in front. Okay, so that's what we got going on there. And we're going to group some of these terms together. 1 minus 1/2, 1/3 minus 1/6, 1/5 minus 1/10. So every denominator, and then we double that and subtract it. And we end up with this variation of really the same sum, right? So 1 minus 1/2 is 1/2. The minus 1/4 stays there. 1/3 minus 1/6 is a 1/6. The minus 1/8 stays there. 1/5 minus a 10th is a 10th, etc. And then if we factor 1/2 out of every single one of these fractions, we end up with 1/2 times, guess what? The original series. So now instead of having a sum of natural log of 2, we just rearranged all the terms and ended up with 1/2 times the natural log of 2, which is extremely bizarre. So that's something that we want to watch out for. We are not necessarily typically going to be finding the exact sum of an alternating series that is conditionally convergent, but this is just something to keep in mind. It's a property of conditionally convergent series that you can rearrange the terms, manipulate them, end up with a totally different sum. Okay, it's still conditionally convergent, but that's one of the reasons why we don't always state the sum of a series, even if it does converge. All right, so that's kind of interesting, but we're going to leave it at that. So go ahead and try the homework, see how it goes. Let me know. Let me know if you have any questions. Thanks for watching. Have a great day.